Here's problem 1317. What is the gravitational force on a 20 kilogram satellite circling the Earth? Radius 6.4 times 10 to the 6 meters, mass 6 times 10 to the 24 kilograms, with a period of 5 hours. So this information is the information on the Earth, not the information on the orbit. And we really need information on the orbit, which we're going to get from Kepler's third law. Period squared should be equal to 4 pi squared over g times the mass of the central body, in this case the Earth, times the radius of the orbit cubed. So if we employ Kepler's third law, we can get the radius of the orbit, and that's what we need. So let's find the period first. We have a period of 5 hours, and there's 3,600 seconds in an hour, so that's going to give us 18,000 seconds as the period or the orbit of this satellite. Now, since Kepler's third law looks like this, period equals 4 pi squared over g times the mass of the central body, in this case the Earth, radius cubed, we can reverse engineer this to find out what the radius is of the orbit. So multiply both sides by gm, divide by 4 pi squared, take the cube root, and so the radius is going to equal g times the mass of the Earth times the period squared divided by 4 pi squared, all of this to the cube root. Alright, so that is going to be equal to 6.67 times 10 to the minus 11 times the mass of the Earth, 6 times 10 to the 24, times the period of the orbit, 18,000 seconds, over 4 pi squared, and all of this to the cube root, or the 1/3 power, if you will, and that is equal to, remembering to square a period for the 18,000 seconds, this is 1.486 times 10 to the 7 meters. The cube root will give us that. So that is the actual radius of our orbit. So if we're looking at the Earth and we have the satellite out here, what we have just calculated is from the center of the Earth to the satellite. That is the radius of our orbit as it's going around the Earth. This is not from the surface of the Earth, but it goes from the center of mass of one to the center of mass of the other. That is the radius of our orbit. We want to find the force on the satellite, and that's given by Newton's law of gravity. Force equals G, mass of the Earth, mass of the satellite, over the distance between the two masses, r squared. In this case, the radius of the orbit. So this force is going to be equal to 6.67 times 10 to the minus 11 times the mass of the Earth, 6 times 10 to the 24, times the mass of the satellite, which is 20 kilograms, all over the radius of the orbit, which we just found to be 1.486 times 10 to the 7, and we'll square that. So this is equal to 36.2 newtons. So that is the force on this satellite at that distance. 36.2 newtons is the force at that radius of orbit.